Okay, so out there in the dark, there's a comet named 3I/Atlas, and it is doing things that, frankly, should be impossible. This isn't just another icy rock hurtling through space. No, this object is basically throwing a wrench into our fundamental understanding of comet physics, giving us a whole series of mysteries that scientists are really struggling with. It's a true cosmic anomaly, and we're about to dive into why. I mean, it sounds like something straight out of science fiction, right? Comets are supposed to be predictable. They follow a clear set of rules, governed by heat, gravity, and the solar wind. They get bright, they fade, their tails do a certain thing. It's all supposed to make sense. But this one, 3I/Atlas, well, it's different. Recent observations show it behaving in ways that completely defy our standard models. It's a cosmic rebel. And it's forcing us to ask, do we really know comets as well as we thought we did? So let's play detective and look at the evidence. All right, our first piece of evidence is the one you can literally see. It's the most striking thing about this comet, its tails. They are absolutely not what we'd expect, and they're the first big clue that something profoundly strange is going on here. A typical comet tail is kinda messy. It's fuzzy, it spreads out, and its activity is all over the place as the sun hits different spots. But Atlas? Just look at this. Its tails are incredibly structured, they're narrow, and they are weirdly stable. For astronomers, that's a major red flag. And this quote just nails it perfectly. This isn't just a slightly more focused tail. We are talking about structures holding their shape like laser beams across millions and millions of miles of empty space. That kind of stability is, well, it's basically unheard of. What's really wild here is the ratio. Not only does it have two tails, but one is always 5 times longer than the other. But the truly bizarre part, the shorter one is an anti-tail. It points towards the sun, flying directly into the solar wind that should be pushing everything away. How is that even possible? Well, to pull that off, to maintain a tail that's fighting against the solar wind for 600,000 miles, the material in it has to be unbelievably dense. In fact, calculations show it needs to be about 1,000,000 times denser than the solar wind itself. That is not the kind of density you get from ice just turning into gas. This points to a completely different and totally unknown mechanism at play. So let's move on to our second clue and see how this mystery deepens. If the tails are weird, the amount of stuff actually creating those tails is an even bigger puzzle. The math just completely falls apart. Okay, just a super quick refresher. Comet Physics 101. Comets get tails because the sun's heat causes their ice to sublimate, right? It turns directly from a solid into a gas, and that gas and dust streams away. The amount of sublimation all depends on the sun's energy and the comet's surface area. So, based on how bright and big its tails are, scientists calculated how much active sublimating surface area 3I/Atlas would need to have. The number they came up with is a massive 620 square miles. But here's the problem. Our best estimates from actually looking at the comet's nucleus put its entire surface area at maybe 35 square miles. So we need 620, but we only have 35. That's a shortfall of 15 to 20 times. It's like the comet is producing an impossible amount of material from a body that's way too small. This is the huge question. The easy answer would be that the comet broke up into lots of little pieces, right? That would increase the total surface area. But high-resolution images show a single, solid, intact nucleus. No fragments, no debris field. The source of this massive outflow of material is a complete and total mystery. And that brings us to our third and final clue. As 3I/Atlas moves away from the sun, it should be getting colder and dimmer. But, you guessed it, it's breaking that rule too, and in a big way. Look, comets follow a really predictable curve. They brighten on their way in toward the sun, and they fade on their way out. Simple. But 3I/Atlas isn't fading. It continues to glow with this intense, sustained brightness, as if something is keeping its engine running at full throttle. To stay that bright, the calculations are just staggering. The comet has to be shedding material at a rate of 200 tons every single second. That's an incredible amount of mass for an object that should be cooling down and going quiet. Let's just walk through the logic here, because it's wild. It maintains a constant glow. To do that, it has to be losing 200 tons of material every second. At that rate, the comet would have shed about 10% of its entire mass in just 2 months. A comet losing that much, that fast, should be visibly falling apart. But observations show the nucleus is still stable and intact. It's a complete paradox. So, where does this all leave us? We've looked at the evidence, and every single clue points away from our standard understanding of how comets are supposed to behave. So, to recap our little investigation, we have impossibly structured tails, a mass loss rate that just doesn't fit the comet's physical size, and a brightness that suggests the object is destroying itself, even though it appears perfectly fine. Any one of these anomalies by itself would be remarkable, but all three together, they paint a picture of an object that is truly breaking all the rules. And that's the ultimate question we're left with. Are we looking at something that isn't a comet at all, but some new class of object we've just never seen before? Or is 3I Atlas a messenger, telling us that our fundamental physics of how comets work is incomplete? Or maybe just plain wrong? For now, the case remains wide open.